Okay, recording has started. So good morning, everybody, and welcome back to Math 115. Early morning this Monday, daylight savings time felt rough. How's everybody doing? Literally woke up 5 minutes ago. Nice. Want my hour back. Yeah, I agree. It's I don't know. Supposedly there was a reason for daylight savings time at one point in time, but I think we've pretty much all but concluded that it's terrible for everyone. But it's just still here for some reason. So I don't know. Maybe we'll abolish it in our lifetimes. Okay, well, happy daylight savings time. Good job making it back to class. If you're here, then you have some mental fortitude. Okay, so, before we get started on the lecture, I graded all of the exams. So I posted your grade to Blackboard, and if you emailed me, or not if you emailed me, if you submitted your exam as a PDF, as was requested, then I was able to get your PDFs onto my iPad, grade them, and then send you the graded PDF via email. Okay, so if you didn't get comments on your exam and you want comments on your exam, then you'll need to come to office hours and talk with me sometime, or we can schedule an appointment outside of office hours, or you can just resend me your exam in a proper format, and then I can give you the comments. And I just did it this way rather than the way that I did it before, because the way that you have to write things on like the Blackboard grader is just really, really bad compared to Notability. So I was like, screw it. I'm just going to download all the exams and grade them all on the iPad. And it worked pretty well. So that is what I did. I really liked all of the stories that you guys had put in the bonus problem, by the way. There were some students who took it in sort of a comedic direction, which was really entertaining, and there were some students who took it in a more serious way, and I tried to respond to most of them. But yeah, good job on those. The average was something like 78, maybe 79, somewhere around there. So a couple points down from the last exam, which was expected, but not too bad. Okay, so last week we kind of started talking about chapter 4, which is all about trigonometry. And we started by talking about what angles are, okay? And then we gradually kind of worked our way towards the unit circle, okay? And we tried to sort of reconcile the two ways of thinking about a point on the unit circle. And the two ways that we had of thinking about it were, well, I can just walk x units to the left, right, and then y units up, and then I'll be at the point x comma y in the plane. And that works fine. But you can also say instead, well, I'm going to angle myself in the direction that I want to go, and then I'm just going to walk one unit away from the origin. Okay, so the correspondence here was between this angle theta, which we only need the angle theta to understand the second method, because we know since it's the unit circle that we have to walk exactly one unit away. And we wanted to reconcile this angle theta with the point x comma y, and we did that using cosine of theta, and sine of theta. Okay, so that was what we did last week. And then we talked a little bit about some other trig functions. And yeah, so this week what we're going to do is we're going to talk more about trigonometry. Okay, we're going to learn about the signs of trigonometric functions. Okay, so when are they positive and negative? We're going to learn about trigonometric identities. Okay, which an identity is just basically an equation where we set thing 1 equal to thing 2. And they're typically characterized by the fact that thing 1 and thing 2 will be quite different, but it turns out that they actually mean the same thing. Okay, so that's what an identity is. And then we're going to talk about which trigonometric functions are even or odd. So we're going to bring back that notion of even and oddness. And then we're going to talk about how we graph trigonometric functions. And that'll pretty much carry us through this week. Before we start, though, are there any questions about either administrative aspects of the course or things we did last week? Okay, if not, then I'm going to actually really quickly go back to week 9 and talk over a couple more examples to get us warmed up for what we're going to talk about today. Okay, so we just finished that one. So this was one of the things that I kind of wanted to get to last week, but I didn't quite have enough time. Okay, so this looks crazy, but let's try to understand what this diagram is telling us. This diagram is basically telling us the most important correspondences, okay, between the points on the unit circle and these angles, which are written inside here. So first of all, every angle here is measured in both degrees and radians. Okay, so that's how we can understand this angle, which is measured up from the positive x-axis as our initial side, always. And for each one of these points, what they've done is essentially drawn in a triangle, okay, a triangle like this. Hopefully you can see that kind of red line there. And they've drawn in this triangle and said, okay, well, here we have a 30-degree angle, and here's a 60-degree angle, and here's a 90-degree angle, and I know that the radius of this is 1, so they used trigonometry. Well, actually, they didn't use trigonometry at all. They just used the Pythagorean Theorem to find out, well, if this side is side length 1, and this is a special 30, 60, 90 triangle, I can figure out that this side length across from the 30 should be 1/2, and this side length across from the 60 should be 1/2 times the square root of 3. So 1/2 times the square root of 3 would be equal to the square root of 3 over 2. And that's how they get this point. Okay, so the way we understand this is that the square root of 3 over 2 is equal to cosine of pi over 6, or cosine of 30 degrees. Okay. Sometimes I'm not going to specify if I write like pi over 6 like this. I don't always specify that that's measured in radians, because it's a little bit implicit that if we're involving pi, it's probably a measurement of radians. So sometimes I just drop off that RAD just because it's cumbersome to write. But what I will try to do is that anytime that I'm ever talking about degrees, I will use this little degree symbol above my 30 here. Okay, so if I don't put the degree symbol and it's an expression involving pi, I'm probably talking about radians. Whoops. Just turned off my iPad by accident. There we go. Okay. So all of these points here are just given by them using the Pythagorean theorem. Okay, so basically for this 120 degree angle, okay, they dropped this line here, and they said, well, if this is 120 degrees, okay, then the rest of the way down to 180 would be an additional 60 degrees, so then this is a 30 degree, and so on and so forth. Okay, they just use these triangles to figure out where these points are on the unit circle. Okay, so this is a good thing that, I might keep handy if I was going to take the exam. This would be a nice document that I would keep nearby so that I can check all of those values there without ever having to really use the Pythagorean theorem too much. But I would encourage you guys to still develop the skill set such that you can find these points without having to use this picture. So that's kind of a useful diagram that tells us all those points. Okay, so now let's do, we're not going to do this one yet. We'll do this one. Okay, just a quick warm-up example. Okay, so we want to find u such that u comma 1/2 is on the unit circle. So let me ask you guys, how can I check this? Or how can I find u? Question for the class. What do we think? We know that u comma 1/2, this point here, should be on the unit circle. So is there something that I can do with that point that would help me determine what u should be? Well, we could. The tricky thing here about involving a trigonometric function is that in order to find the value of a trigonometric function, we would need to know what is the angle which corresponds to this point. Okay, so here's the issue. We have a unit circle, and we know that there's a point on the unit circle. It's 1/2 tall. Okay, so maybe it's somewhere here. We know that this length here is 1/2. And we're trying to understand what is this length here. So you're right, we could understand it if we knew what the angle theta was, then this length here would be cosine of theta. So we could use a trig function if we knew what the angle was, but we don't actually know what the angle is. The only thing we know is that this is a point which is on the unit circle, and its y-coordinate is 1/2. So is there something else I can do here to figure out what this red distance should be? Can someone tell me what is the equation of the unit circle? Two pi r would get us the circumference, but I'm looking for the equation of the unit circle, which is the points x comma y satisfy this equation, then they're on the graph of this unit circle. Remember, equations of circle have the form x minus h squared plus y minus k squared. Kumar, you're getting a little ahead of the class. That's one of the identities we're going to learn later. Is equal to r squared. This is all I'm looking for. Yeah, p of theta is equal to x comma y was our correspondence between points and angles. But again, we're thinking right now maybe we should avoid involving the angle theta just on account of the fact that we don't know what it is. So we would be introducing an additional unknown, and that would be maybe, yeah, you're right. That is more of a relationship or a function even. Okay, what I'm looking for here is just the equation of the unit circle, okay? So if a point x comma y is on the unit circle, it's going to satisfy an equation which looks like this, where remember the unit circle is the one with h comma k, the center of the circle is just 0 comma 0, and the radius of the circle is just 1, so r squared is also 1. So if I use this equation, I get that the equation of the unit circle is x squared plus y squared equals 1. Okay, we should never forget that this is always in the background. Okay? And you can see where it comes from, because look at this triangle here. This is the triangle where this is the y-coordinate, this is the x-coordinate, and then this is 1. So the Pythagorean theorem tells us that x squared plus y squared is equal to 1. We don't even need the formula for the unit circle. We can derive it just by drawing a triangle on the inside. Okay, so x squared plus y squared should be equal to 1 for all the points which are on the unit circle. Which, you know, Kumar was kind of getting at the same thing. I think Abdurrahman put it in earlier in a pretty good way. This one squared is equal to a squared plus 1/2 squared. I think that's going to wind up being our equation that we're going to use once we take this point u comma 1/2 and plug it in to our equation. If it's a point on the unit circle, it must satisfy the equation of the unit circle, right? So I'm going to take u comma 1/2 and I'm going to plug u in for x and I'm going to plug 1/2 in for y, and then I'm going to solve for u. So what do I get? So I'll plug this in and I will get u squared plus 1/2 squared should be equal to 1. And then I will get that u squared should be equal to 1 minus 1/4, because that's what I get when I square a half. So I get u squared is equal to 3/4. So then u should be equal to the square root of the right-hand side. Well, square root of 3/4 is equal to the square root of 3 over the square root of 4, which is equal to the square root of 3 divided by 2. Okay, so it turns out u should be the square root of 3 divided by 2. Okay, and if we want to understand what theta is now, we know that this side length is 1, we know this side length is 1/2, and we know that the bottom side length is square root 3 over 2. Can someone tell me what then should theta be? Yeah, 30 degrees or pi over 6 radians. Okay, so we can figure out theta after a while, but I think going straight to an approach involving an angle when we don't know what the angle is and we're supposed to solve for something which is not an angle is maybe not the best way to start the problem, because you're sort of introducing an additional unknown, and usually we can only really solve things if we just have one equation with one unknown. So for example, if we were to find out some equation like, cosine theta equals u, well, this is true, but the problem is we're trying to find out what u is and we don't know what theta is. So I don't know what the right-hand side is and I don't know what the left-hand side is either. So that will kind of put me in a situation where I can't really progress. So better is to always understand that no matter what we're doing here with trigonometry, okay, the underlying concept which we rely on all of the time to prove things about all of these triangles and these angles and everything is the fact that we're always working on the unit circle, and the unit circle has two properties that we should never ever forget. The first property is that the radius is 1. Okay, so no matter where I draw a radius, if I draw it here, or if I draw it here, or if I draw it here, the length is always 1. That's the most important property. Okay, radius is equal to 1. The second most important property is that if we have a point here, x comma y, then it satisfies the equation x squared plus y squared is equal to 1. This is the equation of a circle at the center 0, 0 with radius 1. Okay, so these are the most important facts that we should remember about the unit circle, and we should, anytime that we get stuck on a problem, I'm telling you that 9 times out of 10, you can use one of these two facts to get yourself unstuck. Okay, if the y is 1/2, then will the x always be square root of 3 over 2? No. There's one other thing that it could be. If we have a y coordinate, have I gotten myself in trouble? You're right. Actually, Sam brings up an extremely good point. I'd made a mistake here. Here's my mistake. When I wrote that when I took the square root of both sides here, I should have gotten plus or minus the square root of 3 over 2. So plus or minus the square root of 3 over 2. And why is that true? Well, that's true because there's another point on the unit circle which has height 1/2. It's the point which has height 1/2 on the other side. And the x-coordinate will be, running out of colors, the x-coordinate will be here at negative square root 3 over 2. Very good point, Sam. So our answer here should be that we get u equals plus or minus square root of 3 over 2. Yeah, in general, for a height, okay, for a height y, we're always going to get this relationship where we get 2 points kind of symmetric across the unit circle. Okay, so for example, here, there's only 2 heights which the unit circle will reach, for which we only get 1 point, and those are the heights +1 and -1. Okay, so those are the points 0, -1, and the points 0, 1. Okay, for those 2 y values, we're only going to get 1 point on the unit circle, but for all the other y values, since we have this kind of symmetry across the y-axis, we are also going to have a negative solution in tandem with our positive solution. How would you know if it was negative or not? Well, the way the question is formulated, we should really give both answers. The question is worded in maybe a not so great way. A better way to word the problem would be to say, find all values of u. Find all values of u such that u, 1/2 is on the unit circle. That might start to get you thinking that there might be more than one. But technically, I mean, if we just say find u such that u, 1/2 is on the unit circle, it's like saying, you know, it's like saying if we say find x so that x squared minus x is equal to 0. Well, you could say x is equal to 0, but that's not the most complete answer. You could say x is equal to 0 or x is equal to 1. Okay? And you might have a better chance of remembering that we should find 2 solutions if I put in all values of x such that this is true. But this is kind of like an implicit assumption that if we are asked to find x such that something about x is true, we should list all of the values of x for which that thing is true. And same thing here with our u. If we're asked to find u such that this point is on the unit circle, we should, in order to give the most complete answer, list all values of u which will make this true. The other way that this question will sometimes be phrased is they'll say, find the value of u such that u, 1/2 is on the unit circle, and then they'll say something like, and u is larger than 0, or something like that. Sometimes they'll say that. And then you can find just 1. So did that answer your question, Savannah? Okay, good. Any other questions about this example? Okay, if you remember one thing from this example, let it be the fact that any point x, y, which is on the unit circle, satisfies the equation x squared plus y squared equals 1. Okay? You can think about this as being the equation of a circle, or you can think about it as being the Pythagorean theorem. It's whatever you feel like. All right, we're gonna skip the next example. We're gonna move on to something new now. Okay. So we're gonna talk about something new now. And that new topic is going to be what we call the signs of the trig functions. Okay, and what I really mean here is kind of like trigonometric inequalities. Okay, so in particular, we're interested mainly in this one here. Okay, we want to know when is a trigonometric function taking a positive value. Okay, so if we ask this question, for which values of theta is sine theta going to be larger than 0? Well, remember, the way I find sine theta is by taking this angle theta. I get this point on the unit circle, which corresponds to it. And I want to know, when is this y value, which is equal to sine theta by definition? Okay, I want to know, when is sine theta larger than 0? Well, that amounts to understanding which values of theta are going to produce a point on the unit circle which lies above the x-axis. Okay, so one of these points here. Okay, but a point, for example, like this would not satisfy the property. Okay, so this theta is no good because it would produce a value of y where we would have y is less than 0, and therefore sine theta is less than 0. Okay, so we want to consider what are the values theta which produce the result we want, which is that the y-coordinate of the point on the unit circle should be above the x-axis. Okay, it should be positive. So let me erase the bad one. Okay, so we see that theta should basically lie in between like a 0-degree angle or 1-degree angle or whatever. And what's the largest that it should possibly be? Well, it should be anything which is smaller than an angle which went all the way across, right? So here's how we write such a thing. We would write theta, okay, which is my angle. It should be larger than 0, okay? Because if I have a 0-degree angle, then the corresponding point on the unit circle would be, so 0 angle gives us the point here, which is 1, 0. And we want to know, when is the y value larger than 0? That would produce equal to 0. Okay, so let me move this down a little bit, and let's formulate this a little bit better. We'll say that sine of theta is larger than 0 if theta should be larger than 0 degrees, but it should be smaller than 180 degrees. Okay, or we could write 0 should be less than, theta should be less than pi radians. Okay, so these are the values of theta which will produce a positive value for sine theta. Okay, and then if we want to know when is sine of theta equal to 0, well, this will happen basically at these two lime green points, or yellow green points, right? It'll happen when the y value is 0 on our unit circle, which happens in exactly two places. It happens at the point 1, 0 and the point -1, 0. So sine of theta will be equal to 0 if theta is exactly equal to 0 degrees, or if theta is exactly equal to 180 degrees, respectively. 0 radians and pi radians. Okay, and then finally sine of theta will be less than 0 if theta is between 180 degrees and 360 degrees, or pi less than theta less than 2 pi. Okay, so this is how we do this entire analysis of where is sine going to be larger than 0 or equal to 0 or less than 0. And by where, I'm really referring to for which angles theta is sine going to produce a positive result, negative result, or a 0 result. Okay? And we're sort of interested in understanding this for all of our different trigonometric functions. Okay? So we're going to consider the values theta which produce a y value which is above the x-axis. We're going to consider for which values of theta do we get an x value which is positive. So that would mean all of the points on the right half of this semicircle. So that's going to correspond to our cosine case. Okay, our tangent case is going to decide, okay, when is the ratio between y and x positive? Okay, that'll happen when x and y are both positive or when x and y are both negative, and so on and so forth. So we're going to get all of these different things nailed out. And the following diagram is how we're going to kind of, man, what the hell is going on with the iPad? Okay. The following diagram is going to kind of explain things for us. Okay, so this is going to describe where each trigonometric function is positive. Okay, and here's how it works. So first of all, let me remind you that if we have a coordinate plane, okay, we have 4 different quadrants. By quadrants, I'm referring to basically one section. So for example, this section here, okay, we call this quadrant 1. We use a big Roman numeral 1. This one's quadrant 2. This is quadrant 3. And this is quadrant 4. Okay, and this diagram tells us which quadrants are the basic 3 trigonometric functions going to be positive in. Okay, so this one is all. So sine, cosine, and tangent will all be positive for values of theta which have a terminal side ending in quadrant 1. Okay, then if we have an angle here with a terminal side which ends in quadrant 2, okay, then we're going to get a point on the unit circle x comma y such that only the y coordinate is positive because the x coordinate will also be negative. And then since we divide a positive by a negative, tangent will also be negative. So sine is the only positive trigonometric function for angles which terminate in the second quadrant. Okay, then if we're in the third quadrant, our xy, our coordinates, is going to be both negative. So if we do tangent, which remember is equal to the y divided by the x, then this is going to be larger than 0 because we take a negative number and divide it by a negative number, we get a positive number. So in this region, tangent will be positive and all the rest will be negative. And then finally in quadrant 4, we're going to see that a point which would be on the unit circle, would have a positive x coordinate but a negative y coordinate. And that means that the only positive trigonometric function in quadrant 4 will be cosine. Okay. So this diagram tells us which trig functions are positive in which quadrants, okay? And the acronym is, we consider it going like, we go in the order of the quadrants. So 1, and then 2, and then 3, and then 4. Okay, so quadrant 1, we get A. So that's for all. Quadrant 2, we get S. That's for students. T is for take. C is for calculus. So all students take calculus. Okay, which you guys haven't gotten there yet, but maybe you will. It's just a way of remembering the diagram. Okay, so if you remember all students take calculus, you'll be able to quickly answer where any of these trigonometric functions are positive or negative. Okay, so ASTC. Okay, so here are the things written out. Okay, all trigonometric functions are positive for angles theta whose terminal side lies in quadrant 1. Okay, so if my terminal side of my angle theta lies in quadrant 1, then all of the trig functions will be positive. And then all these other bullet points are just saying the same thing. Sine of theta is positive in quadrant 2, tangent is positive in quadrant 3, and cosine is positive in quadrant 4. All right. So it's a little bit different than you might be used to thinking, you know, just from like literature, you've learned to read left to right and then down, right? So you'd think SATC, but we're actually considering this in terms of how the angle progresses if we are to take this angle like this and move it around in this counterclockwise fashion. Okay, in the counterclockwise fashion, if we start here at 0, we go at first into quadrant 1, that's A. Then second, we go into quadrant 2, that's sine. Then third, we go into the third quadrant, that's tangent. And then fourth, we go into this final quadrant, which is cosine. So we read ASTC like this. Okay, questions about ASTC? All right, if not, I'm going to move on and talk about something else. Okay, so what is it? We're going to talk about reference angles. Okay, and this is going to kind of be related to the topic which we've already talked about, which is when our angle is going to be coterminal. Okay? So here's what a reference angle is. Okay, we let theta be any angle. Okay, so theta could be anything. It could be 1 degree, or it could be 1,000,000,000 degrees, or it could be negative 10,000 radians. It could be any kind of angle that we want, and it can go around the circle as many times as it wants. It's just, we're gonna sort of consider where does it end up facing, okay? So that's what the reference angle is. So the reference angle of theta is going to be the unique coterminal angle theta prime. Okay, so when I write this apostrophe here, okay, sometimes we say prime in math. So theta prime, which comes from theta, such that theta prime is going to be an angle which is between 0 and 360, or it's going to be in radians, it's going to be between 0 and 2 pi. Okay, so what do I mean by that? I mean, okay, if we have theta equals 21 prime, okay? Not 21 prime, sorry, 21 pi. What does that mean? Well, the angle theta says 21 pi, that's 20 pi plus 1 pi, and 20 pi says basically 10 times 2 pi plus 1 pi. So this part says go all the way around 10 times, then halfway around. So if we were to draw theta, it would look like this. We'd go around like 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 and a half. So here's theta. Okay, I probably should have chosen a slightly less spinny angle. Okay, but then the reference angle here, theta prime, is going to be an angle which faces in the same direction. So the end result of theta, remember, is that eventually it's facing in the negative x direction. Okay, so this is the terminal side of theta. The reference angle of theta is going to be the angle theta prime, which is coterminal to theta, but does less spinning action. Okay, so it's just going to be the angle here, which just says, okay, rather than go around 10 times and then go around half, I'm just going to go around half, and then I'll end up facing in the same exact direction as the other angle. Okay, so this one's theta prime. Okay, so this is about reference angles. We just take angles which are sort of needlessly spinning like crazy too many times around the unit circle. We say, okay, look, I don't care how many times you spin around the circle. I just care where you end up. So I'm going to work instead with this reference angle theta prime, which ends up facing in the same direction as theta, and so therefore has all of the same properties, except I don't have to draw a million spirals in order to draw the angle. Okay, so this is a reference angle. Okay, so that's about reference angles. So here's a GIF for you guys. It's Captain America. Okay, so maybe we should try one more reference angle and then we'll call it for today. I don't think I have time to get into the periodicity stuff. So let's try finding theta prime if theta is equal to negative 80 degrees. Okay, so I would draw initially my unit circle. And what does negative 80 degrees look like? Well, it's a little bit less than negative 90 degrees. So negative 90 degrees would be, okay, we start at the positive x-axis and then we go down, 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 down until we form a perfect corner. So negative 80 degrees is going to look like a little bit less than that. So it's going to be this angle theta here. So here's theta, negative 80 degrees. Okay, what is going on here? There we go. So this is our angle theta, and we want to find theta prime. And here's the deal. We need theta prime to be an angle which is between 0 degrees and 360 degrees, which ends up on the same exact terminal side. Okay? So since I can't actually have a negative angle, okay, because remember theta should be larger than 0 degrees, I need to consider a positive angle which has the same terminal side. So what I'm going to do is I'm just going to start going around until I hit the same terminal side. Okay, and the property of theta is that theta should be somewhere between 0 spins and 1 full spin, right? That's what theta prime says. It says it should be between 0 degrees and 360 degrees. Okay, so I just go around until I hit that terminal side, and I call this theta. Okay, theta prime, excuse me. So I knew that since theta was negative 80 degrees, I know that theta prime will be, I go all the way around less 80, so I get theta prime equals 360 degrees minus 80 degrees is equal to 280 degrees. So a little bit more than 3/4 of the way around the circle. That's how I can think about it. Okay, so this is how we find reference angles. All right, that's it for today. Thanks, everybody. Sorry, I went 1 minute over. We'll pick up with this tomorrow. If you have questions or if you want to learn more about this stuff, please stay after class. I have office hours from now until 10:30. Thanks, Heidi, too.